Okay, here we've got the notes for section 3 for stats, which starts on the bottom of this page, sorry. So section 2 dealt with measures of center. Section 3 is going to deal with measures of variation, which tells you how this data is spread out. So the first one and the easiest one to calculate is the range. So the range of a set of data values is the difference between the maximum and the minimum values. So you take the biggest value, subtract the smallest value, there you go. So find the range of these numbers. So same set we've been using before. So 26 is the largest, minus the smallest 22. So the range is 4. And that's as easy as it can be. Okay. So that then brings us to the ones that get more complicated, the standard deviation. So this fun formula here gives you the standard deviation for a sample. So S for sample, because we're using a sample, we use the English letter. So you have the square root, the sum of each number minus the average squared. So we need to calculate the average first. Then we will take each value, subtract the average, and square it, and add that list of numbers up. Divide by n minus 1, so 1 less than the number of numbers we have, and then take the square root of that whole thing. So here we've got some properties. Measures how far they differ from the mean. It's usually positive. It'll never be negative. It might be 0. It has to be positive because you're taking a square root, and square roots can't generate negative solutions. Or you're making, I guess they can, but you can't take the square root of a negative number. But since S is measuring the distance from the mean, that's why it's always positive. It's 0 if they're all the same number. So as you start to include outliers, you can really change the value for S. The unit is the same as the original data value. So if you're measuring minutes, their standard deviation is in minutes. So it's referred to a biased estimator, which we'll talk about what that means. It just means it doesn't do a very good job of finding the whole population value. So here it says find the standard deviation of these numbers of chocolate chips. So we actually did that earlier. The first thing we're going to need is actually the average, which we did way back in example 1 of the previous section. So the average of these values is 23.4. So we're going to jot this down real quick. X bar is 23.4. So what I'm going to need to do is I'm going to take this formula, I'm going to take each measurement, so 22 minus 23.4, so measurement minus average, square it, and then continue this process and add them all up. Now because we're squaring, these will all come out to be positive numbers. Notice that they don't have to be in order, so which is nice. Oops, 23.4 squared. So I'm just gonna, this string here is just this top of this fraction, so I'm gonna work this out first, and then we'll come back and get the rest of it. So 22 minus 23.4 squared plus 22 minus 23.4 squared plus, oops, parentheses, 26 minus 23.4 squared. If you're typing this in your calculator, you do type it in exactly as I have it written down. Those parentheses are necessary. So this whole big string comes out to be 11.04. So now we're going to do this formula. So S is equal to the square root. So I just calculated the top, 1104. The bottom is n minus 1. So I have 1, 2, 3, 4 measurements. So n minus 1 is going to be 3. So I need to divide it by 3. So this is the square root of 3.68. And then take the square root, and I get the value of 1.92. So this kind of gives you an estimate of how far away most of the measurements are within 2 of the average. And if you look, that gets me up to 25.4 and down to 21, so I cover almost all my values. Down here at the bottom, you've got the range rule of thumb. This is used to find the maximum, minimum, usual values. So when you say, well, that measurement's unusual, or that is expected, kind of, these are your things. So the minimum usual value, you take the average and you subtract 2 standard deviations. So here, if we round that up to 4, a cookie would have a usual, it wouldn't be too few to assume that we would have 19. Maximum is you add 2 standard deviations, so we assume that to be 2. Again, we double, we get 4, so 27 would be like the upper limit for if you get more than 27 chips in your cookie, that's a pretty chocolate chippy cookie. You can do an estimation here. You divide the range by 4. So that didn't work very well on this one because the range here was 4. 4 divided by 4 is 1, and this is almost twice that value. But the more measurements you have, the better this estimation factor becomes. Okay, so we got a couple examples. So it says using the 40 chocolate chip counts from Chips Ahoy cookies in table 1, way back at the beginning of the chapter. The average is 24, so we're going to jot this down. X bar equals 24.0, and the standard deviation S is 2.6. I use the range rule of thumb to find the minimum and maximum usual numbers. So to find the minimum, you take your average and you subtract 2 standard deviations. So 24 minus 2 times 2.6. That is 18.8. To find the maximum usual value, you take your average and you add 2 standard deviations. So 24 plus 2 times 2.6. So that gives us 29.2. So then determine whether a cookie with 30 chocolate chips is unusual. So 30 is unusual because it is more than my maximum value. Anything less than 18.8 would be unusual. So example 4 just asks us to use the range rule of thumb to estimate S. So they give you the min and the max. So the estimation is S equals, or approximately, the range divided by 4. So I need to find the range first. So the range is just the difference between those two numbers. So that's 11. So 11 over 4. Oops. Is 2.75. You notice in this case, when we took all 40 measurements, our estimation is 2.75. The actual value up here in the problem was 2.6. So that's actually not too bad of an estimation. But this, you need to have a lot of measurements. You can't do it with just 2 or 3. Down here, we have the equation for if you're talking about a whole population, meaning you measured everyone. So you're using sigma instead of S because Greek letters are for populations. And the only other difference here, so measurement minus, that's the mean for a population. So the top is the same. The bottom of though is the total number of measurements you've made. At the very bottom here, we've got the variance. The variance is just the standard deviation squared. So for a sample, it's S squared. For a population, it's sigma squared. So for variance, we've got the properties here. So since it's a squared, the units of variance are squares of the unit. So if your measurements are in minutes, the variance is measured in minutes squared, so on and so forth. So just like before, when you have some outliers, that does skew the variance a lot. Variance is an unbiased estimator, which makes it good at estimating the actual population. So if you measure a sample, the variance of your sample will probably be pretty close to the variance of your entire population. That's not true for standard deviation. The standard deviation of the population will not probably give you a good estimation of the actual standard deviation. So here we have for a bell-shaped distribution. So it just gives you bell shape means it follows a nice curve. You might have seen this graph before in another math class. That's a big peak in the center like this. This value right here is the average. And as you move away from the average, you get fewer, less, fewer, more. So think about heights. Most people are pretty close to average heights, but as you move away, you get fewer and fewer people. As you get very, very, very tall, fewer people. As you get very, very short, fewer people. So this gives you the range. So about 68% of the entire population will fall within one standard deviation, up and down. So it's a range. So 68% would fall within that measurement. And then if you go out another one, that gives you 95. You go out another one again, that gives you 99.7% of everyone. So here we have example 5. IQ scores have a bell-shaped distribution with a mean of 100 and a standard deviation of 15. What percent of IQ scores are between 70 and 130? So I'm not going to draw my curve. So my average goes in the center, and you count by standard deviations. So going up would be 115, going up again would be 130, going down would be, let's see here, 85, and going down again would be 70. So if you look here, that's 1, 2 up, that's 1, 2 down, and up here, 2 standard deviations is about 95%. So 95% of the population would have IQ scores between 70 and 130. Almost everyone. Down here, at the bottom, you have Chebyshev's theorem. This is just kind of a very quick estimation method. It says at least 3/4 of all values lie within 2 standard deviations. So notice this is 75%. We set up here that it was 68%. That's at least 75%. Could be better, and at least 89% lie within 3 standard deviations. So here, same problem. So it says the mean is always at least 1 minus 1 over k squared, where k is any positive number greater than 1. So 2 and 3, k is counting the number of standard deviations. So this is just giving you, so 75% is within 1. So between 85 to 115, at least 89% is within 2 standard deviations, which would be, sorry, this is 2. So this would be 70 to 130, and 89% would be going out one more time, so that would be 55 to, I don't know, 145. So there you go. We don't usually use Chebyshev's just because it's easier to use this one up here, but it's something to talk about. Okay, so the last thing we've got here is comparing variation to some populations. So usually you can't compare if you have different units, different things like that, just because the calculations don't work correctly. So here you have the coefficient of variation, CV. So for a sample, it's the standard deviation divided by the average, then times 100. So, but this lets you compare things that are not necessarily measured in the same way. So here, example 7, compare the variation numbers of chocolate chips using the sample data. So for cookies, our CV will be, so on the bottom we have our average, so 24.0. I'm off the bottom of the screen, sorry. On the top, you've got S, which is 2.6, and we're going to multiply that by 100%. And for the Coke, same thing, their CV. On the bottom, you have the bar, 0.81682, and on top, the S value, 0.00751, and once again, times 100 because we're making everything a percent. So for the cookies, 2.6 divided by 24 times 100 is 10.83%. 0.00751 divided by 682 times 100 is 0.92%. So if you notice, the 10% variation, almost 11 versus not even 1%, which means what this is saying is we're comparing the number of chips in cookies has about 11% in variation, whereas the Coke cans vary not even 1% by weight, which makes sense. You can only put so much Coke in the can. The cookies are, it's a lot easier to get a different number of cookies just because of where you pull from the dough or the batter or whatever you have. But the Coke cans all are very, very close in weight to each other. And to wrap it all up, we've got the discussion of biased and unbiased estimators. So a biased estimator does not tell you, the sample does not tell you very much about the actual population, or doesn't estimate it well. So standard deviation is a biased estimator. The value of S for a mere sample does not give you a good estimate of sigma of the population. The variance is unbiased. Variance S squared will give you a good estimate of sigma squared for the entire population. And that wraps this section up.